Hey guys, so welcome to part 2 of Geometrical Isomerism. And so in this video we're going to continue the cases in which geometrical isomerism can arise. So our third case is in substituted cycloalkanes. So when it comes to substituted cycloalkanes, just make sure to have at least 2 carbons which are sp3 and are substituted. And these substitutions can be shown in either wedge bonds or dash bonds. And wedge and dash basically show the orientation, whether it's towards the viewer or away from the viewer. That's what a wedge and dash bond show. So let's get to some examples so that you'd get familiarized with the usage of these bonds and also GI in substituted alkanes. So our first example is cyclopentane with 2 wedge bonds. Now, what would be a geometrical isomer of this? Well, a geometrical isomer of this would basically be that. Now, anything else that you draw, like let's just say that you drew this compound, but instead of a dash here, you drew a dash here. So, okay, let me just specify. This here and this are the exact same. Because this compound is quite symmetrical, these two would be identical, and hence there's no need of mentioning it again. There's no point in it. Now, if you were to mention this compound, this is also the same because, if you flip the compound over, like let's just say right now it's facing one side and you flip it over on the other side, then you would get this compound. For example, let's just say this is some form of that cyclopentane that we have. It's like laying flat on a surface. Now, these bonds, the wedge bonds, would be shown in some sort of way that, makes it seem like it's sticking up towards you. Like this. Now, if we were to draw the same thing, but in a dash bond, they would go down like this. Okay, So, if you flip this compound over, by 180 degrees, you would get this compound. And similarly, if you flip this compound over by 180 degrees, you would get this compound. So, basically, if you get 2 of these down, all the other possibilities are somewhat identical to the first 2. So this here is identical to that, and switching these bonds would also be identical to the initial as well. So yeah, the geometrical isomers for a di-substituted cyclopentane would be this. Di-substituted with methyl groups would be that. Or actually, let's write the IUPAC name for this. This would be, let's say this is, I'm going to write the locants. 1, 2, 3, 4, 5. So this is 1, 2. And these are methyls. If they don't indicate anything, it's a bond line structure, right? So it would be the usual. So this would be 1, 2 dimethyl cyclopentane. Cyclo because it's a cyclic compound, and pentane because there are 5 carbons with no double bonds or triple bonds. So the geometrical isomers of this compound would be these two right here. Notice that the difference between these two structures is the fact that the groups are are arranged spatially different. One of them is towards you and the other one's away from you. They're not differing in structure, but rather the spatial arrangement of the groups. That's something important to realize here. So our next case in the geometrical isomerism cases is the double bond in cyclic compound case. So for a double bonded cyclic compound, there must be at least 8 carbons in the ring for it to show geometrical isomerism. So let's take an example. I'm first going to draw a cyclohexane with a single double bond, like this. And these are hydrogens. I'm just going to draw that for our clarity. Now, when you're looking at this compound, you may think that since the groups attached on either carbon on either side of the double bond is different, it can show geometrical isomerism. However, when this shows geometrical isomerism, for example, this would be our cis isomer, because like groups are on the same side of the bond. So this would be our cis isomer. So now let's draw our trans isomer. So we've got this. Okay, wait, let me draw these properly. A hydrogen here and a hydrogen here. And this is our double bond. So this would be our trans isomer. So as you can see, there is a lot of bending, and what we like to call in organic chemistry or in chemistry in general is angle strain. So this right here has a lot of angle strain. And angle strain isn't exactly a favorable thing. So it's like really not wanted in a compound, and hence this does not exhibit geometrical isomerism. So no GI. Now this would be what we call cis and trans, however it does not exist practically due to angle strain. So what about an 8-membered carbon chain? 8-membered carbon ring. So what about an 8-membered carbon ring? So let's draw that as well. I'm going to draw it a little below so that we have space. So the first one that I drew, this looks kind of weird, okay. This one would be our cis isomer. Now our trans isomer would be something like that. Yeah, so this would be a trans isomer. So one thing that you want to remember is that as the number of carbons increases in the cyclic compound, the less angle strain there will be in the cis-trans isomerism thing. So here, when there's 6 carbons, we have a lot of angle strain. However, in this one, we have less angle strain, but it's not completely gone yet. There's still a little bit. So this is just a little less. Now for angle strain to fully go away, so for angle strain to fully go away, we need at least 11 carbons. So for angle strain to fully be gone, we need 11 carbons present in our cyclic compound. So that's when you can say that officially there's no angle strain restricting the geometrical isomerism. Now here also geometrical isomerism is exhibited, but not as much due to angle strain. Here it's not exhibited at all because of angle strain. So that's how you can find geometrical isomerism in double bonded compounds in cyclic compounds. So let's first start off with an example. So let's go with an example, and that's going to be propadiene. Okay, so why don't you try drawing the structure for this compound, propadiene. So prop means 3 carbons, and ene means that there's a double bond. But how many double bonds is given by this di here? That means there are 2 double bonds. So this compound is most likely this. But if we were to draw this in, the structural way, CH2, double bond C, double bond CH2. So that's what we're dealing with here. Now let's check the hybridization of these carbons. So just a quick thing to remember, when a carbon is single bonded, it's sp3 hybridization. When there's a double bond somewhere, then that carbon would be sp2. When there's a triple bond, that carbon would be sp. And also, this case would also be sp. So that's just a quick hybridization recap. But yeah, so this carbon right here would be sp2. It's sp2. And this would also be sp2. And this would be sp. Now when it comes to that, you can automatically think about the orbitals which are, doing the bonding here. So now when it comes to these carbons right here, which are sp2 hybridized, we'll talk about those carbons first. We know that when a carbon is sp2 hybridized, it implies that there are 3 sp2 orbitals. And we also know that in an sp2 orbital, the composition is 1 s orbital and 2 p orbitals, which combine to make 3 sp2 orbitals. We've discussed this in the chemical bonding series. Now, when it comes to this, we know that there is 1 p orbital which is left. So there's 1 pure p which is left. Now these sp2 hybrid orbitals, these will undergo sigma bonds, while this one is the one that causes pi bonds. So yeah, so let's just take this carbon right here. I'm gonna break it down. So we've got hydrogen and a double bond. So this, and one of these bonds is made up of one of the orbital on the carbon contributing side is sp2, and here the carbon H overlap will be sigma sp2s, and this is also sigma sp2s. And the carbon one of them is a sigma sp2 sp2, and the other one is pi pp. So those are the bonds that occur in this area. But let's first discuss the sp hybridized carbon, and then we'll get on to how geometrical isomerism even arises here. So as I've said, sp2 hybridized means that there are 3 sp2 orbitals, right? Similarly, when it comes to an sp hybridized, there will be 2 sp orbitals which contribute to sigma bonds, and 2 pure p orbitals which contribute to pi bonds. So when we come to how the bonding in this arises, we have to keep these 2 things in mind and draw the sigma and pi bonds respectively. So let's draw the full structure of this, expand this whole thing right here. So I'm gonna go down. Okay. So first, we've got carbon. There are 3 carbons since this is probadiene, so there will be 3 carbons. There is a H on this side, and this side, and that side. Okay, so we've got all of our sigma bonds down. So the lines here represent our sigma bonds. Now let's talk about the pi bonds. I'm going to draw the orbitals here. Okay, so now we've got all the p orbitals drawn, and this is all the orbitals and the sigma bonds. So now let's talk about the overlapping present. So there'll be 1 pi bond like this, overlapping between the blue p orbitals, and there will be another pi bond like this with overlapping between the red p orbitals. So yeah, now we've got these what do you call them, this structure showing the pi bonds and the sigma bonds. Now let's draw it with planes so that we know the orientation of these hydrogens back here. So the geometrical isomerism is shown in the form of different orientations of these hydrogens. So now what I'm going to do is that I'm going to draw the structure using planes. So the same structure right here. We're going to draw carbon, sigma bond, carbon, sigma bond, carbon. Now, from this, we know that one of these, if you check this pi bond here, this red p orbital pi bond, that pi bond looks like it's in the z-axis. For example, so this is x, y, and z. So this one right here looks like it's along the z-axis. So what I'm going to do is I'm going to draw a plane that looks like it's in the z-axis. Like that. Okay. Next, we're going to draw the one for the blue pi bonds. If you check the blue, that looks like it's along the y-axis, along this. So what we're going to do is that we're going to draw a plane which seems to be in the y-axis, or along the y-axis, parallel to the y-axis. Okay, so now we're going to focus on the hydrogens. So let's first talk about the hydrogens present on this carbon. So let's look at this carbon right here. I'm going to highlight it. This carbon right here is our primary focus right now. So one thing that you should remember when it comes to that carbon right there is that it is sp2 hybridized. So this is sp2 hybridized, which is something that we've already understood earlier, and out of which this carbon can make 4 bonds. 4 bonds can be made by a carbon in this compound, right? In any compound. And so these 4 bonds, we're going to write down how they're taken up. So how these 4 bonds are satisfied is what we're going to write down first. So obviously between this carbon and this carbon, there are 2 bonds. One is a sigma bond, and 1 pi bond between the carbon and carbon. And the other 2 bonds are taken up as 2 sigma bonds between carbon and hydrogen. So we've got one like full bond down. Like basically that's 2 bonds, but we've got in a double bond which is down. We've got that fixed. But the other 2 bonds, the hydrogens, we don't know which orientation they're supposed to be in. So that's what we're going to find out, or which plane the hydrogens are supposed to be in. So when it comes to an sp2 carbon, we know that sp2, no matter what atom it is, if it's sp2, it has a certain shape. So this shape for an sp2 is trigonal planar. So we've got a trigonal planar structure or shape for an sp2 carbon. Now when we fixed this bond right here, this carbon double bond carbon is fixed in its orientation. So this is fixed. Now, how would we get a trigonal planar? We would get a trigonal planar by putting this up, one hydrogen up, and the other hydrogen down. So they would just be right above each other, above and below. So in that way, you would get a trigonal planar structure or shape for that, sp2 carbon right there. So let's move on to the other carbon, which is this. This one will have no hydrogens because all 4 of its bonds are satisfied by the double bonds. So here is where we will get those hydrogens. So now we're focusing on this carbon right here. And once again, it's the same thing. We know that this is sp2. This is an sp2 carbon. And, the same conditions apply for this carbon as well. So if this bond is taken, this is a double bond between carbon, and that bond is fixed in its orientation or its position. So that bond is fixed in its plane. Now, how else would we get a trigonal planar structure? So with respect to this plane, we would get a trigonal planar structure if one hydrogen was towards us and one hydrogen is away from us. Remember that you have to check according to the plane given. So this plane, according to that plane, what would be our trigonal planar thing. And another thing to remember is that these hydrogens are always in a plane perpendicular to the consecutive plane right before it. So that's why we directly concluded that this would be above and below instead of any other orientation. Just remember that when it comes to these type of questions, get the planes of the carbons down. Just draw down those planes. And the next thing that you should remember is that the hydrogens, these hydrogens right here, which are attached to the carbon, are in perpendicular planes compared to the previous plane between the carbon and carbon. Like, no matter what, they will always be in a plane that is perpendicular. So these planes will always be, like, if you had, okay, so in this compound, we only had 3 carbons present. There's only 3 carbons here. But for compounds with 4 carbons or 5 carbons, the plane pattern will still be this. It'll still be the blue plane, the red plane, and blue plane, red plane. It'll still continue in that same pattern. So yeah. Now, one thing that you want to remember here is that this compound does not show geometrical isomerism. So no GI. And that's because these hydrogens right here, this hydrogen and these hydrogens, are not in the same plane. And because they're not in the same plane, this compound does not exhibit geometrical isomerism. So now let's try another one. We'll try a alene with 4 carbons instead. And why don't you try and figure out whether or not the compound can show geometrical isomerism. Okay, so here are the bonds drawn for a 4-membered alene, and as you can see, the type of p orbitals are repeating in a pattern. First it's the blue p orbitals, then it's the red p orbitals, and then it's the blue p orbitals again. So because of this, you will also see a similar pattern in the planes in which these atoms are present. So let's draw the planes using this. I'm gonna first draw the carbons. Okay, so now let's draw these planes. Now the first plane that we want to see is that this blue plane right here. These p orbitals are present in a plane like that. So that's what I'm going to do. And the next plane that we have is this red plane right there. So we're going to draw that plane too. And finally, we have this other blue plane, which is in the same orientation as this one. Okay, so now we have the planes present drawn. So we have this blue plane and the red plane and the blue plane again. Now one thing that you want to remember is that in allenes, this plane pattern is present. So we'll always have these two planes repeating in a pattern over and over again until the end carbon. So that's one thing that you want to remember. That's the first point. And the second point is that these hydrogens, the hydrogens present at the ends of the compound, are always in a plane which is perpendicular to the plane of the carbon that it's attached to. So let's specify. If you take this plane right here, this blue plane, if the hydrogens are supposed to be in a plane which is perpendicular to this blue plane, that means the hydrogens have to be present in a plane which is parallel to this red plane. So how would the hydrogens be present? They would be present in, let me draw them. As a wedge and dash bond. One hydrogen is towards you and the other one is away from you. Now similarly on the other side, since it's the same blue plane, we can similarly say that there would be a wedge and dash bond. Directly. And now, since these hydrogens are on the same plane, which is a plane that is perpendicular to the red plane, we can say that this shows GI, or geometrical isomerism. Now, one thing that you should, okay, let's just compare this compound right here to the previous one. In the previous one, if we use the same 2 points, one of them is the pattern of planes, which is always one plane and the other plane are perpendicular to each other, and that pattern will repeat. That's 1 point. Here we don't need to think about that because there are only 2 planes present. And the other point is that the hydrogens, or the plane of the hydrogens, is perpendicular to the plane of the carbon to which they are attached. So if we take this red plane here and we look at these hydrogens, those hydrogens have to be perpendicular to that red plane, or have to be present in a plane which is perpendicular to that red plane. So that plane would be a plane which is parallel to this blue plane, right? So because of that, we now know that the hydrogens should be in this orientation. Now similarly on the other side, we can look at the blue side, which is already discussed in this example. So allenes, we can now think of a short form or a shortcut, because when we looked at this compound with only 3 carbons, this propadiene, when we looked at that, we saw that it does not exhibit geometrical isomerism because the hydrogens are not in the same plane. But when it came to a 4-carbon allene, we saw that it does exhibit geometrical isomerism because the hydrogens are in the same plane. So one thing that you could just shorthandedly remember is that a polyene with an odd number of double bonds can show geometrical isomerism. So let me write that down here. Polyenes with odd number of double bonds can show GI. So either it's an odd number of double bonds, either this, or even number of carbons. You could remember it either way. So yeah, that's all about the allenes and polyenes showing geometrical isomerism. Now the 6th and final case is in spiro compounds. Now spiro compounds are compounds which are consisting of 2 or more cyclic rings which are attached at a single carbon. So let's just look at a quick example. So spiral compounds could be something like this. One thing that you have to remember though for geometrical isomerism in spiral compounds is that it's pretty similar to the ones in polyenes. Just take these rings to be considered as double bonds. So let's just go with an example and hopefully you'll understand better with that. Okay, so this is a compound right here, and as I said before, if we convert or write all of these cycles or rings as double bonds, we would get this compound. So, as we've studied before, just the previous case, we know that this does not show GI, and hence this also does not show geometrical isomerism. So similarly with spiral compounds, you can consider these, rings to be considered as double bonds. And when you consider them as double bonds, just once again do this, convert them all into double bonds and do the same thing that we did in allenes to understand whether or not it shows geometrical isomerism. So yeah. So finally, we've finished the types or the cases of geometrical isomerism. Now here's some pointers that you could use when it comes to a bigger compound and they ask like how many geometrical isomers are possible. When those types of questions come, it could be kind of time-taking to check each and every site of geometrical isomerism and see if it's possible or not. So instead, you could just directly use these formulas right there that I've written. And yeah. So basically, in an unsymmetrical molecule, if there are n geometrical isomerism sites present, then the number of geometrical isomers would be 2 to the nth power. So if there's a symmetrical symmetrical compound, and n is even, then the number of geometrical isomers would be 2 to the power of n minus 1 minus 2 to the power of n over 2 minus 1. If n is odd, then the number of geometrical isomers would be 2 to the power of n minus 1 minus 2 to the power of n minus 1 over 2. So yeah, you could use these formulas to give you a quick answer during your examinations and whatnot. So that's it for geometrical isomerism, and if you have any doubts, you could put them down in the comment section. In the next video, we will be talking about optical isomerism, which is another type of stereoisomerism. So yeah, stay tuned for that video. That's it for today.